Hi everyone, here's your experiment 4, which is ether synthesis of phenacetin, and we call it as Williamson ether synthesis because the name of the scientist who found this method is Williamson. Okay, so purpose of this experiment is synthesize phenacetin from acetaminophen. Phenacetin has an ether functional group. Acetaminophen has an alcohol functional group. So we're going to put that alcohol and another alkyl halide to form an ether. Okay. Learning objectives, you're going to learn how to perform a Williamson ether synthesis and safely work with bromoethane. And this is, if you want to synthesize an ether, this is the most simplest form. Okay, and this was named after the Alexander Williamson. He is the person who discovered this reaction in 1850s, long time ago. Okay, now this is what's happening during this reaction. So basically, alcohol in the form of an alkoxide ion react with, so this is your alcohol. First we have to form an alkoxide anion, and then it's going to react with alkyl halide to form the ether, and this is the ether functional group. Normally alkoxides are strong nucleophiles that tend to react via SN2 mechanism. So recall that the strong nucleophiles, they would like to react via SN2 mechanism. So what would be a good substrate for SN2 mechanism in terms of primary, secondary, tertiary alkyl halides? Normally for the SN2, since it's a bimolecular nucleophilic reaction, it would like to have very open substrate, meaning less sterically hindered. So primary halides would be the most appropriate for SN2 mechanism. So because of that, it would love to react with the primary alkyl halide. Okay. In a traditional Williamson ether synthesis, alkoxide is generated by reacting sodium hydride. So this is sodium hydride with an alcohol. So you can see here with the sodium hydride and alcohol, it's going to form the alkoxide anion, and at the same time it generates hydrogen. So hydrogen, if you generate hydrogen in a reaction, that's not going to be a good situation because it can pose a fire hazard. Okay, it is possible for hydrogen gas to ignite. So because of that, we are not going to take that risk. So we're going to form our alkoxide using sodium hydroxide as the base instead of sodium hydride. So sodium hydroxide is a friendly base. We have it in our labs. We have worked with it. So it's not generate hydrogen when we react with sodium hydroxide. Okay. And these are the millimolar masses given to us. Bromoethane, acetaminophen, phenacetin. Density also given, boiling points and melting points. Okay. Okay, and these are the safety information, and this is how we are going to set up the experiment. So you're going to weigh out 10 millimoles, which is about 150 gram of acetaminophen, into a 50 milliliter round bottom flask. So you take the round bottom flask and then you put 50 milliliter, 10 millimoles, which is about 1.5 grams of acetaminophen into the flask. And then you're going to add 10 milliliters methanol. 10 milliliters methanol. Methanol is the solvent. So we need to have an organic. We need to have a solvent that can dissolve your organic compound, which is acetaminophen, as well as that would be also able to react an aqueous base like sodium hydroxide. So methanol is a good solvent for that. So you add 10 milliliters methanol. And then secure the flasks so it can heat and stir simultaneously. So you can put it on a hot plate, and then you put a stir bar, magnetic stir bar, so you can start stirring. And we are going to perform this reaction in a water bath, so we can control the heat without evaporating methanol, our solvent. Okay. So you're going to set the hot plate to 150 to 200 degrees Celsius. and you're going to heat it under a water bath, on a water bath. And you also need to add our base, which is a sodium hydroxide, 50% sodium hydroxide, about 10 to 12 drops. You're going to put it into the flask, and then you put a heating condenser on top of this. You will see this setup in your virtual lab. Okay, and then water in, water out. So you put the condenser. So you're going to be doing heating and refluxing. What it does is, so when you do the heating and the refluxing, so the reaction mixture will heat, and when you do the refluxing, meaning the vapor will go along the condenser, but it would not evaporate. Since you have a condenser, it will drop down back. So we can keep the solvent inside the reaction flask. At the same time, we can heat it. So that is the purpose of having a condenser while it is being refluxed. But if you do the reaction without a condenser, what's going to happen? All the methanol will evaporate, and also your other components when acetylene, based on the boiling point, it can also evaporate. So by having a condenser on top of the reacting flask, we can heat it without losing any of our solvents. Okay, so you're going to do that for how long? For certain time, maybe it's over there. And then what you go, so in this first step, what are you doing in the first step? So let's look at our reaction. So our reaction is, so you're going to react acetaminophen. Acetaminophen is this molecule. It has an amide group, CH3, and also it has a OH. So this is acetaminophen or Tylenol. So in the first part, what you're doing is you're making the alkoxide anion by reacting with sodium hydroxide. So sodium hydroxide is a base, hydroxide. Hydroxide ion goes and take up that hydrogen, acidic hydrogen, and give its 2 electrons to oxygen. So it's going to form this alkoxide anion. That's what happening in the first step when you add sodium hydroxide in the presence of methanol, alkoxide anion. Now we created a strong nucleophile, alkoxide anion O minus. Now the next step is you're going to be adding your alkyl halide. Okay, so you can see here. So okay, so after you add sodium hydroxide, you're going to stir until the mixture, which is acetaminophen, completely dissolves. Okay, and then you're going to remove the condenser, and then using a pipette, you're going to be carefully adding 20 millimoles of bromoethane to the flask. So bromoethane is going to be your primary alkyl halide substrate that the alkoxide is going to react. And then you're going to heat the mixture to a gentle reflux for another 1 to 1.5 hours for reaction to complete. And after the reflux is done, you're going to remove the heat source, add water from the from your water bath down the condenser, and briefly stir the mixture. You're going to be adding hot water. Okay, so when you add hot water, what happened? You just made organic compound, which is your phenacetine. So now I will show you what happened when you add bromoethane. Okay, so let's look at what's going to happen. Now you have this alkoxide ion made, and then you're going to be adding now ethyl bromide, which is CH3 CH2Br. You add 20 millimole of that. We're going to be adding more of this. Okay, and then here you have alkoxide ion, so there's two reaction take place. So the alkoxide anion goes to this primary carbon and then remove bromide. Okay, so your product is going to be now phenacetin, which is nothing happened to this group. It's going to stay there, and then the O oxygen will take that ethyl group CH2CH3. Now we have just made an ether. Okay, and then sodium bromide also would be formed. Now this is ether we just made, which is also phenacetin. Okay, now you can see this phenacetin is an organic molecule. When you add water, what's going to happen? It's going to crystallize us out. Okay, because it's not going to be soluble in water. So you add hot water and then you will see the crystals start forming, beautiful shiny crystals. Okay, it'll happen fast. Once crystal appear, place a reaction flask in an ice bath for 10 minutes to maximize the process of crystal formation. And then you're going to vacuum filter the crystals and wash with cold water to get rid of any sodium hydroxide, any other impurities trapped inside the crystals. You're going to wash it with cold water, and then you're going to store the crystal until dry, and then you're going to weigh it and determine the melting point range of the product. Okay, that is the experiment that you're going to watch in your virtual lab. Okay. Okay. And the pre-lab question, draw a mechanism for the reaction conduct in today's experiment. When it says it's today's experiment, you have to write down the proper reactants and the reagents that we used. So this is the generic equation that is given to us. Alcohol reacting with sodium hydride, giving you sodium methoxide and hydrogen gas. That is the formation of the alkoxide ion. And then the alkoxide ion reacting with alkyl halide is given with this one. So this is not what you're going to write when it says what is today's reaction that you did. So you have to refer it to the acetaminophen reacting with sodium hydroxide, and then formation of the alkoxide anion, and then the alkoxide anion reacting with ethyl bromide, meaning this is what you need to explain. I just explained it over here. Okay, how the experiment is being done and what's happening when you add reagents to your reactants. So you have to put together all that and have to draw a mechanism for the reaction conducted in today's experiment. You can do it yourself and check to see if you also get the same thing I'm getting. So this is your acetaminophen, which is, you have an amide group over here, and then you have OH. Now you have to draw the mechanism, not just the reagents, and then you add sodium hydroxide, just like I explained earlier. Sodium hydroxide and methanol is going to be your solvent. Okay, so sodium hydroxide, there are two lone pairs, so hydroxide is a good base. So you take that and then gonna go ahead and get this hydrogen from the alcohol. Alcohol hydrogen is acidic enough, the base can remove that, and then you're going to be making your alkoxide anion, which is this one, O Na. Sodium would be positively charged and oxygen would be negatively charged, sodium alkoxide. Okay, and then the next step is you are adding ethyl bromide, CH3, CH2, Br, primary alkyl halide. It's going to react in SN2 fashion. Alkoxide anion goes and attack the primary carbon. The bond between carbon and bromide breaks, and you're just going to form your product, which is this. OCH2 CH3. So this is acetaminophen. No, phenacetin. This is phenacetin, and this one is acetaminophen. So that is the mechanism for the formation of ether with alcohol and alkyl halide. Okay, and plus you will also make sodium bromide. So you can also write down that plus sodium bromide, NaBr. Okay, no hydrogen gas generation. So that is the first part. And is the Williamson ether synthesis SN1 or SN2 reaction? You know that. We talk about it. It's SN2 reaction. And how do you explain it? Because alkoxide in a Williamson ether synthesis, we have to make an alkoxide, and alkoxide is going to be a nucleophile, and normally alkoxides are very strong nucleophiles. So the strong nucleophiles tend to react in SN2 fashion. Okay, so because of that, Williamson ether synthesis is an SN2 reaction. What is the purpose of the sodium hydroxide in this reaction? What do you think? So sodium hydroxide is the base, right? If you don't add sodium hydroxide, what's going to happen? So then the alcohol of the acetaminophen remain as alcohol without forming the alkoxide ion. It cannot react as a strong nucleophile unless we make the alkoxide ion. So sodium hydroxide is the base that would create the alkoxide ion by deprotonating the alcohol of the acetaminophen. It's going to take that acidic hydrogen. Okay, so that is the purpose of the sodium hydroxide and the theoretical yield and percent yield for this reaction. Now we have done this several times. You guys know how to calculate the theoretical yield. Remember, we use 10 millimoles of your acetaminophen, so the molar ratio is going to be 1 to 1, isn't it? It's going to be 1 to 1. 1 mole of acetaminophen will give you 1 mole of phenacetin. So if you start, but we use 20 millimoles of ethyl bromide. So which one is a limiting reactant? Ethyl bromide or the acetaminophen? Whichever the lowest number of moles would be the limiting reactant, and that is the amount of product that you're going to be forming. Okay, so you started with 10 millimoles of this, 10 millimoles of that, and 20 millimoles of this. So the limiting reactant is going to be, where did you jump? So 20 millimoles. So acetaminophen is going to be the limiting reactant. That's the amount of phenacetin that you are going to make, 10 millimoles, 1 to 1 ratio. Okay. So then how do you find the theoretical yield? If you know that the 10 millimoles is the amount that is going to form, so we can find out the theoretical yield. Theoretical yield, yes. So 10 millimoles. So we know 10 to the power 3 millimoles is 1 mole, converting millimoles to moles. And then 1 mole of phenacetin is the molar mass of phenacetin, which is 179, I believe. Yes, 179 grams. So that is the molar mass of phenacetin, not Tylenol. Okay, so this will give you theoretical yield as 1.79 grams. Now I would like you to do this calculation in your report sheet. Don't just write down 1.79, but show me how you did it. It's right here. Okay, you can just have to rewrite it. Okay, and then that is a theoretical yield. But how would you calculate the percent yield? Percent yield is going to be actual yield over theoretical yield times 100. Actual yield you can find out from the virtual video. Okay, and then write down, and then you divide that number by 1.79 times 100 will give you the percent yield. We also talk about how to calculate that, so you can refer to that. And then what are some possible sources of error in this experiment that could lead to a lower yield of the product? Well, watch the video and see where are the places that can lower the percent yield. So many things can take place. I mean, when you're adding sodium hydroxide, if the alkoxide ion, if all the Tylenol or the acetaminophen does not convert to alkoxide ion, with sodium hydroxide, then Not all Tylenol would be able to react with ethyl bromide. So that's one thing, right? One reason that we would not get the product that we want if we do not keep the heat source properly, having the correct temperature, because this temperature also plays a role when when the reactions are taking place. So just think about the places that can go wrong or maybe can lower the yield, and just come up with some ideas of your own. You can think as a chemist, as a scientist, and just be creative and come up with some reasons. Okay, all right, that's it then. Bye bye.